the webinar to our keynote speaker, Steve Schlehuber.
All right, thank you, Brian, and good afternoon, everyone. My name is Steve Schlehuber. It's a pleasure to be with you all today to discuss time to market in reference to insert molding. I work with a lot of engineers and designers day in and day out, and I realize the importance of education for custom molded parts to ensure that the best design is moving forward as quickly as possible. So today, we're going to discuss in depth the insert molding process. All right, on your screen, you should see our agenda page, and I'm going to go through each one of these so you kind of know what we're going to talk about. The first is, what is insert molding? We want to talk about the concept, what's involved. The second thing is, we're going to talk about the benefits of insert molding. Why do we use it, especially from a design and engineering standpoint? What's the importance of insert molding in our process? We'll talk guidelines for standard inserts, and we'll also talk guidelines for custom inserts. This is a real meat of what we're going to talk about and why it's important to know these things. We'll also talk material considerations. Many people don't think about that with insert molding, so we're going to discuss the importance of that. And we'll also talk file preparation. This is the actual critical part, so we definitely want to cover that as well. So what is insert molding? Essentially, this is a fairly simple process. It's where we take a molded part, we take some kind of metal, whether it's a standard threaded insert or some type of custom insert that's been designed, and we want to try to implement those in one process. In this case, it's the molding process, where we take two pieces and ultimately they become one part. So we're going to get into this in depth, but first thing I want to do is we're actually going to look at some actual physical parts. And I'm going to bring this up one by one. And these are all different scenarios. They're all unique. Some are custom, some are standard. The first part that we're going to look at is basically a standard housing. This part has standard inserts involved. There's nothing custom about these inserts. As you can see, their locations are highlighted as I point them out on here. These are all on the ejection side of the tool. They're standard threads. I know you can't see the threads in there, but that's the type of insert that they are. Now, the unique thing about this part is not only do we have standard inserts on the ejection side of the tool, but if I can get this rotated around, there we go. You can see we have actually two locations on the front side of this where we have inserts put as well. And the challenging thing that we have with these type of inserts on the front half is keeping them in place. This part right here has something that bolts on and it comes off. So there's actually a closed insert. The back side of this does not go through. It's very hard to keep these inserts in place. We had one of these that worked very well, and we had one of these that did not work very well. And you have to make a decision of whether or not insert molding works for this part in this specific scenario. And we talked with the designer and the engineer on this, and we came to a solution. So this is one form of an inserted molded part. All right, we'll get into the second one. Now this is a custom molded insert. This right here is actually a cannula tube. It's a medical grade or a medical based product. We did the molding right here on this purple portion. This is a very custom part that's designed just like any other part. It's not your standard insert. We have some fine shutoff right here on the tube to make sure that no plastic moves into the cylinder portion of this. And you have another fine shutoff on this side. So fairly standard custom insert molded part. Yeah. All right, let's get into the last one here. This is our fairly complex insert molded part. To give you some background on this, these dark portions right here, this is the insert molded portion of this. This is the metal, and this bluish portion here, that's the actual molded resin. Now, one thing to take away from this is you see these inserts. There's not much surface area. There's not a lot to grab onto. Typically, this type of insert molding would need to be done in most likely a vertical press. That's something that's challenging. Not a lot of molders out there have something like that. We talked with our designer or engineer on this project, and we actually came up with a solution to use side actions or hand loads to pinch this insert and then we were able to figure out a way to run this in a horizontal press. Very complex insert molding process, but we were able to formulate these into the process, and we had success with it. We'll talk a little bit about this more in the rest of the slide. All right, so now that we got to look at some parts, we want to look at the benefits of insert molding. The first benefit that we see is it reduces assembly. This is a very important thing, especially for designers and engineers when they're thinking about their overall final assembly. They're thinking about that final part. We want to take one of the steps out of the process. A lot of times with standard inserts, people are inserting them after they get their molded part. That's time consuming, it's costly, it could add a middleman in there. We're trying to reduce that out of the overall process. So by being able to mold, whether a custom or standard insert, we really take down the time. And when we're talking time to market, that's everything. We want you to get the part, assemble it, be ready to go. The second is increased reliability. There's nothing better than taking a metal piece and having that plastic mold around it to create the strongest bond possible. We want to make sure that when your assembly goes together, there's no cracking, there's no breaking, there's no stripping. The reliability of that insert inside the molded part is key. And when you have a very complex assembly at the very end of your project or whatever you're working on, we want to make sure it's as reliable as it possibly can be. The third is design flexibility. When we talk to designers and engineers, we constantly want to give them the flexibility to design their part however they want to. We don't want to restrict them. And a lot of times, there's metal with plastic. We deal with a lot of parts that go from metal into the plastic to try to reduce weight. They want to reduce the process or the assembly. So giving you the design flexibility to say, hey, we can mold these inserts into your part, that's very key. That's a huge advantage for someone who's a designer or engineer and they have that flexibility. Now, are there any negatives to using inserts for the molding process? There are some, but they're few. Regulations, every now and then we run across maybe a medical regulation, or if you have to test the actual plastic before the metal is implemented, you may have a restriction. And typically this depends on the industry that you're in. The second is molding issues. Sometimes we do see areas of the part that just are not fit for inserts. If you have a very tall boss on the part, sometimes by putting an insert at the end of that boss for, say, a standard screw, you reduce our ability to core out that boss all the way down to the part. This could create sink on the front surface. If it's cosmetic, that could create an issue. Not to mention you could potentially cause warp or other issues. Now, if there's no room in the plastic for insert, there's no reason to try to fit an insert in where you're going to create a molding issue with it. If it has mating parts or it has circuit boards in a housing that are just tightening up everything else, don't try to force something to be molded into it. That's going to create thin areas in the molding process, which could ultimately have molding issues. So what are the types of standard molded inserts? As you can see on the screen, we have two different kinds. We have stainless steel ones down here, and these are brass. They're all diamond patterned, or they have some type of pattern. That's on there so that when we mold these into the material, it really clings to the insert so that it doesn't come out. And these are designed to be that way. They're designed to be strong. They're going to take a hard screw coming in, and instead of trying to go into actual plastic that's threaded, these give you the strength of the actual metal that's on there. Now, what are the guidelines for these standard molded inserts that we just looked at? The insert should be rounded. We want to make sure that they don't have any sharp corners. Inserts should be flush. When we are putting together a tool, we want to make sure that the insert isn't sticking out of the part, grabbing onto the mold and creating some type of hard molding condition. We want to make sure that they're going to be nice and flush. So that's the way that they should be designed in. You want to make sure that they're flush with the top surface of the part. Now, the depth of the mold beneath the insert, we want to make sure that that depth is about 1/6 of the insert diameter. And the reason is to avoid sink. We don't want to create any thick areas. We have a little illustration down here at the bottom. This portion right here is the insert. This is your part below it. We want to make sure we're not creating any thick issues below it. This is a very important one, especially with standard inserts. A lot of people ask us this question, and we tell designers and engineers all the time, make sure it's at least 1.5 times the insert diameter. So as you can see down here, if you have a boss that's coming up out of your part and you're planning on putting an insert, make sure that outside diameter is at least 1.5 times that insert diameter in the middle. This is going to ensure that we can flow around that. That's very important to make sure that we have a good solid molding condition around the insert and we have enough room for it. So what are the types of custom molded inserts that we can use? Bushings, there's all kinds of bushings out there. We see many shapes and forms of them. Connectors, whether they're electrical or some other form of connector. Drill bits, drill guides, other forms of guides, typically these are medical. We actually see needles. These are a very custom form of an insert. Some types of tubing, as you see up here. You can get metal tubing. We looked at a cannula. That was a custom insert on that previous part. We also overmold magnets. This is a very custom. There's a demagnetization process that happens with these, so we're very critical on overmolding magnets. We also have inserts that are very technical and require hand loads to be put into the tools. We're able to do that as well. And then you also have parts like we discussed previously. I showed you that part that was typically done in a horizontal press. You have those that have very little surface area. They can be complicated. They require hand loads and side actions to do those. Now let's switch over and talk about the guidelines for custom molded inserts. The first one, follow the same design considerations that you have for standard. You want to make sure you have enough material flowing around it. You want to make sure that you basically have enough room. You're not creating thick areas that cause sink. Same thing that you follow with standard, follow that for the custom molded inserts. Shut-off is critical. Shut-off on a custom molded insert is everything. When that cavity and core close on each other, you have to make sure that there's a tight grip of the insert. It cannot move. When that plastic flows through and around it, you want to make sure the insert's not going to move around. It's not going to do anything. You've designed the part, you've engineered that part to make sure that it's within one area. So the shut-off is critical. We want to make sure we're able to hold on to it. If it's not a tight grip in there, there has to be shut-off with the cavity and core together. One of the notes, this next note, is we need a contact point, and this is part of being able to shut off with the core and cavity. If we have a molded insert or a custom insert and we're trying to mold over top of it, we have to be able to load it into the tool before that tool closes to shoot the plastic over top of it. So sometimes we'll use pins as locators. Sometimes we'll ask that you design in a feature that we can slide the insert onto the actual mold and keep it in place until that closes. When we looked at the one that needed a vertical press, that one really didn't have anything that we could slide on. That's why we had to use 2 hand loads to close it and keep it and pinch while we put it into the tool. So there's got to be a contact point. Standard inserts are easy because we just load them onto a steel pin. That's simple. But custom, they can come in all forms, shapes, and sizes. So we have to keep that in mind when we're in that design and engineering process. They must be loaded into the tool. They have to hang there and stay in place. Problematic inserts are inserts that move under pressure. These are thin metal insert wires, very hard to hold on to. They're thin, small electrical connectors. These are ones that you could practically bend with your fingers, and we see thin stamped inserts. Stamp parts are really hard. I had a designer that I worked with on a part who had a very thin stainless steel insert. And the issue was we weren't going to hold on to very much of it in the tool while we molded over top of it. And what happened is that insert would literally just bend under the pressure and it would float right to the surface. We see this. If you can actually take your insert that you want to use and bend it and move it, that's going to happen inside the tool. Thousands of pounds of pressure of material are going to require that is going to move around. So we do locators, we do pins to hold it in place, we want to make sure that insert just does not move. So these are problematic inserts, and it's not that you can't mold them. They just take a lot more design and a lot more engineering on the front end to make sure that they're successful. All right, material considerations. This is a big part. A lot of people don't think about this when they're insert molding, but you can utilize a stress chain chart. There's always data out there to kind of show you what's going to happen with that. Materials with low shrink rate work a lot better. So you have to remember that your metal piece, whether it's custom or standard, is never going to shrink in the molding process. No matter how much you heat it up, it's just not going to shrink. However, materials do shrink. And if they cover a large portion of what your metal insert or custom insert is, that insert's not going to shrink and the material is going to try to shrink over top of it. This can create stress, it can create other types of issues, it can crack, lots of things can happen with this. So we want to make sure that we use a lower shrink rate material. And typically these are tough and grade resins. They have a higher elongation, greater resistance to stress and cracking. Typically this is a glass filled material. We actually gave some examples. Nylons, like I said, typically glass filled. Polycarbonates, ABS, PC ABS, these have a lower shrink rate. They're not going to move a whole lot after you mold them. They're going to stick with your custom molded insert that you have. The bad ones are polypropylene, polyethylene. You know, these ones have very high shrink rates. They're very tough to mold in that condition. And one other thing to note too is if you were on here for our overmolding webinar that we did, you know, we talked a lot about materials and how that works with a cold substrate. It's a hard flow. So keep that in mind as well when you're looking at your custom insert molded. When we're flowing that material over top of it, that's a cold insert, whether it's metal or whatever other type of material. The more material you put over top of that insert, the longer it has to flow over a cold surface rather than a hot mold. So give it its wall thickness, make sure you're following those material guidelines, and make sure you're getting the right material to work with your part. So what type of materials can you use for your inserts? Standard are usually brass, stainless steel, sometimes ceramic. If we're looking at custom inserts, we're going to look at aluminum, ceramic, copper, magnets. We're going to look at any type of material that can withstand the pressure and the temperature of the injection molding process. I've actually worked with engineers and designers that we molded certain types of wires and stuff like that that do not hold up into the actual molding process. And a lot of times, you know, we're looking at time to market for this. So whatever type of metal you have that we can work into this process, it's whatever benefits your engineering. File preparation. This is the last thing we're going to talk about. This is important though. The insert CAD must be present in the final design. And we require this, but you're going to want this as well. You need to see where your inserts are going to take up room and how much space is left over. Be very careful of thin areas that are created by the metal insert. Beware of thick areas that are created by the metal insert. We require this because we want to do DFM on the part. I talked to a lot of designers and engineers where we're discussing moldability. We're going to evaluate those thin areas, thick areas. We're going to evaluate how much surface area is being covered by the insert and the material to make sure that you're going to have a good molding condition once we get it into the press. And this is required for custom inserts just so we can validate the shutoff. We want to see how we're going to hold it in the tool. Is it going to stay where it's going to be under pressure? We try to think about a lot of this on the back end or on the front end so we don't have to think about it on the back end. All right, well, let's go through a summary. Insert molding, it can reduce the assembly and the weight of your part. Just be aware of the potential issues that can come up. If it fits the process, design it that way. Engineer it so that it can help you. Standard molded inserts, be sure to follow these guidelines. Make sure you got enough plastic below your insert. Make sure the boss is thick enough to handle that standard insert. For the custom molded inserts, we want to follow the same tips for the standard. Make sure you're keeping in mind those same things, but think about shutoff. Shutoff is critical. How are we going to hold this insert in place? How are we going to make sure that the cavity and core Don't allow your insert to move. Then we're going to think about the materials. The lower shrink rates are better. The nylons, the glass fills, polycarbonate, ABS, PC ABS, these are all great resins to use. Insert materials, you see them all here: brass, stainless steel, ceramic, copper, but ultimately it's any material that can withstand the injection process. So when you guys are engineering, when you're designing, go nuts with it. Put in whatever type of metal piece you have. We'll evaluate it. You do the DFM, make sure all these molding guidelines are followed, and you should have a successful process with it. Insert CAD must be present. Design it in from the beginning. Don't just call out the area that you think it's going to go into. Visually see this within your design. You have to make sure you're looking for those thin areas, problematic areas where you could see sink, warping, any of the above. Make sure that that's in the process from the beginning. All right.
Good stuff, Steve. I wanted to point out that a summary PDF of this webinar is available in the handout section of your control panel, which I believe you can download directly from the control panel, as well as a little quick information on eccentric mold. But I think we have a couple questions here that we can answer. The first one here is how to have an insert that is completely surrounded by plastic. How do you do that, Steve?
That's a really good question. You know, honestly, we get a lot of parts that are designed and engineered that way. The problem is we did talk about the process of being able to hold that in place and keeping that insert where it needs to go. Really, in the prototyping and when we're thinking time to market and we want to get a design like that done very quickly, you can go to a two-shot process. And what that is you basically stick half the insert in, mold over half of it, and then you're going to do another molding process with what you just molded and shoot the other half of it. That's complex. It's almost into an overmolding process. It can be done. But if not, if you can have any part of that insert showing, typically we can use some very small pins to kind of locate it and hold it in place. And we can kind of help on that engineering and design process. But that is a hard process to go about. And typically, in, like I said, time to market, quick turn, that's typically how you could do it.
Okay, very good. The next question is how are PEEK and glass-filled PEEK for insert molding? How does that work?
Typically, you know, PEEK is a high temperature material. We do work with that, and I've talked with engineers and designers about that process. And glass-filled is definitely better. It has a less shrink rate on it, so obviously, you know, that would work with it. But PEEK ultimately is not a bad decision. You know, as far as Ultims and PEEKs and those type of materials, we do see a lot of those working with inserts. So I would say it's not a bad idea. Just make sure the design guidelines are followed, like we talked about, and yeah, design it with the PEEK, with the glass filled, whatever.
All right, we got time for one more here. This one just came in. If I need a mold with inserts to survive a wide temperature range, say negative 30 degrees Celsius to 140 degrees Celsius, is differential expansion an issue to avoid molding or breakage or failure?
Well, I think a lot of this has to do with the actual resin grade that you're going to be using. This isn't so much the actual insert that's going to be put into play, it's the actual resin, the plastic. There's going to be certain materials out there that aren't going to they're not going to react to those temperatures as much, so I would really recommend talking with a material expert. These people will guide you into a material that's going to work well. As long as the shrink is low and it's not going to absorb moisture. Moisture is typically what makes a part go up and down in those different types of degrees. So I would just really focus on that material, and as long as you get the right material, put that insert in just how you want it, and you should have success with it.
Okay, well, that about wraps it up, and I want to thank you for joining us at this webinar. If you have any questions or interest in eccentric products, please visit our website here. You can use our social channels or contact us directly at the number and email listed on your screen. As I mentioned, a recorded version of this webinar along with the answers to all the questions will be sent within 48 hours, so you can expect that as well. Thank you again. We will now sign off in 3, 2, 1.